Good morning. My name is Tracy Reddick, and welcome to American Iron and Steel Institute's review of mixed material joining research results from the Auto Steel Partnership. At this time, I'd like to introduce John Catterall, Vice President, Automotive Program for AISI. John?
Good morning, everybody. I'd like to introduce our guest presenter today. It's going to be Brian Masick. He's a Senior Technical Specialist in the Product Development Organization at FCA. Brian will be walking us through mixed material joining research results from the Auto Steel Partnership. The Auto Steel Partnership is a collaborative consortium between steel, OEM, and Tier 1 suppliers. Together, they perform R&D work to apply new advanced high-strength steels into automobiles. Brian's actually been doing a lot of work with ASP and AISI in the recent past. Brian specializes in lightweighting, advanced high-strength steel structures, and joining technologies. He leads multiple innovation projects within FCA, as well as external collaboration with organizations such as the Auto Steel Partnership and the Lightweight Materials Consortium. Brian has been with FCA since 2012. He previously worked with several Tier 1 automotive and defense suppliers. He holds bachelor's and master's degrees from the University of Toledo in engineering and has been an SAE member for 20 years. And now we will hear from Brian and the launch of AISI's mixed material joining research results headed up by our Auto Steel Partnership. Welcome, Brian.
Thank you, John. I would like to start out by thanking my team, which made this possible and is made up of members from both our OEM membership and our steelmaking membership. And I'd like to extend special thanks to Wendy Dillingham, our project manager. When we started out this project, we had a couple of goals in mind. The first was to enable our OEM members to be able to implement mixed material joining. And for this project, that basically means aluminum to steel joining in any application that suits their particular business models with some level of engineering confidence and backed up by some good research. The second goal was to take the information generated by this project and put it into a knowledge base that's accessible by our members to serve as a stepping off point for any future research, as well as a resource for anybody who is interested in going more deeply into what we have studied. And then finally, we wanted our methodology for this project to be extensible to future technologies and future materials, such that it's relatively easy to compare results between studies without having to redo a lot of work. This was a two-phase project, and the results I'm presenting today are from the second phase. The first phase was to generate a short list of technologies to study. And we did that by generating a matrix of test conditions. This was put together by our OEM members and intended to represent a joint either between a roof and a body in white or a body side and a body in white. And we came up with a number of gauge and grade selections, and then for each stack we replaced the bake hardenable steel class A surface with an aluminum sheet, and we filled the matrix with all of the currently known joining technologies and a variety of test types, primarily a lap shear and a cross tension, and configured in 2 thickness and 3 thickness with and without structural adhesives. We then did quasi-static testing on all of these joints to establish, relatively speaking, how strong they were compared to a baseline resistance spot weld. Doing that let us filter down to 3 technologies to carry on into phase 2. And I'll speak more about these technologies in a moment, but we settled on resistance element welding, friction riveting, and solid self-piercing rivets. Going into phase 2, we took those 3 technologies, and for 2 of them, we added a second supplier so we could compare variations within the technology. Then we repeated the quasi-static testing to both include the new supplier's products as well as check the calibration on our existing suppliers. Then we took all of them through both a cyclic fatigue test and a corrosion test to finish the evaluation. Because these joining methods are coming from joining suppliers with various trade names, we didn't want to be endorsing any particular supplier or trade name as part of this project. So we have adopted some generic terminology, which I will use throughout this presentation. I think you are all sufficiently familiar with resistance spot welding, so I'm not going to dwell on that. The three technologies that we are studying specifically are a solid self-piercing rivet, which is, much like it sounds, a rivet that punches through the stack of 2 or 3 materials, ejecting slugs out the bottom side, and is then upset to form a mechanical joint. It's essentially a cold rivet that makes its own holes. The second technology is a friction rivet, which is a rotary process that spins up a steel joining element to enough speed and temperature that it's able to plasticize the top aluminum layer, push the aluminum out of the way, and then friction weld to the second layer. Because this is a friction weld and essentially a surface solid state joint, it only works on 2 thickness joints, which you'll see in the later tables. And then finally, we studied resistance element welds. This is again a steel joining element that is punched through the aluminum sheet, mechanically clinched or fastened into place by interlocking, and then is resistance welded to the underlying steel sheets by either a resistance spot weld or projection weld, depending on the geometry of the particular element. For phase 2, we concentrated on the lap shear coupons because they were most suitable for the cyclic fatigue testing that we went through. As you can see, we used a 45 by 105 coupon for these. But I mainly want to direct your attention to the 3 thickness joint configuration and the way that we applied the adhesive or sealers. In each case, we applied a structural adhesive or a non-structural sealer between the aluminum top sheet and the steel mid sheet. That was because of considerations for galvanic corrosion, and that is important in our 3 thickness joints because in the 3 thickness joints, we actually pulled the top sheet and mid sheet together. And that means that for the strength performance of the joint, they do not benefit in any way from the adhesive or sealer. We're actually using them as more of a noise factor to understand how well the joining method works to join the 2 steel layers with an aluminum layer on top, and how much the adhesive might be a detriment to the process. Here are some selections from our baseline joints. In each case, for all of our 6 joints, we constructed resistance spot weld baselines and used them to set our performance goals. In the upper left-hand corner, you will see a 2 thickness joint without any kind of sealer or adhesive, and that's a pretty classic spot weld nugget that you can see. The upper right is the same joint, but with a structural adhesive added. And you can see the failure mode there is moved into the top sheet because the combination of structural adhesive plus resistance spot weld was stronger than the top sheet was. And in the bottom, you see a 3 thickness joint with, again, a fairly classic weld nugget pull failure mode. These are the same 3 joints, but they're tested in cyclic fatigue instead of quasi-static pull. The failure modes remain essentially the same, but you can see from the shape they exhibit more of a brittle failure behavior, which is typical for cyclic fatigue. So again, we are pulling a nugget on the 2T, we are failing the top sheet on the 2T with adhesive, and we are pulling a nugget on the 3 thickness. This is our first mixed material joint, and this is the solid self-piercing rivet, as I described before. These are the same 3 joints that I showed before, but in each case, the top sheet of 0.7 millimeter bake hardened steel is replaced by 1.2 millimeters of 6000 series aluminum. In the upper left, it's a 2-thickness joint, but we have added a non-structural sealer to mitigate galvanic corrosion. And you can see the failure mode is very similar to the resistant spot weld. The top right is the same joint with a structural adhesive, and the failure mode, again, is in the top sheet. And the bottom is the 3-thickness joint without adhesive, and the failure mode pulls through the top 2 sheets more or less the way it did in the resistant spot weld. These are the same 3 joints in cyclic fatigue, and here we see some differences from the baseline. In the top left, and I will preface this by saying the way we developed the loading for the cyclic fatigue was we tested the baseline resistant spot weld joints and found out what level of cyclic stress would cause a failure in that joint in approximately 100,000 cycles. And we set that across all joining methods for that joint. So at the stress level that produced a failure at 100,000 cycles for resistant spot weld, in this case, the solid self-pierce rivet plus aluminum sheet and sealer actually didn't fail at 100,000 cycles and went out to a 1,000,000 cycle run out without failing. However, on the upper right-hand side with the structural adhesive, we'll see the failure mode actually changes, and we see a failure at the rivet where the stress concentration is instead of failing the top sheet. And in the bottom sheet, it is, again, somewhat different because we are failing by pulling a nugget out of the bottom sheet rather than the cracking through the top sheet. This is a table showing the results for all of these stacks with the solid self-piercing rivet. And I know this is a little bit of a complicated table, so I will walk you through it piece by piece. There are actually 3 tables here. There's a peak load table where we measured the maximum amount of force experienced in pulling the joint to failure. The second table is the energy at break table, which is the total energy absorbed going through failure of the joint. And finally, the cyclic is the comparison at the 100,000 cycle load between the resistant spot weld and the mixed material joint. There are 6 joints there. I identify as joints 1 through 6. Joints 1 and 2 are 2 thickness. Joints 3 through 6 are 3 thickness. These 6 joints are the same throughout all tests and all joint types, so I will only have to explain them for you once. We use a selection of materials including bake-hardened steel, press-hardened steel, multi-phase 980 steel, and dual-phase 590 steel for these joints in a variety of thicknesses you can see in this chart. The color coding is all versus the resistance spot weld. So if the result was 100% or better of the resistance spot weld value, it is green. If it's 80% or better, it is yellow, 60% is orange, and below 60 is red. So of course, the entire column for resistance spot weld is green because it's 100% of itself. So starting with the peak load results, what we found with the solid self-pierce rivet, the quasi-static peak load was directly comparable to the resistant spot weld in the 2 thickness joints. So those results are green. We saw more variable performance in the 3 thickness joints, and it was really sensitive to the bottom layer thickness. So in the thinner materials, in the 1 and 1.2 millimeter range, we saw some reduced strength performance, but in the relatively thick 1.6, it was comparable to the resistance spot weld. Moving down to the energy results, we saw that in the 2 thickness, there was some reduction in effectiveness in the adhesive joints, but not dramatically so in most cases. But interestingly, in this one, is that in the 3 thickness joints, even though we saw some peak load reduction, the energy absorption was actually equal to or better than the resistance spot weld baseline in every 3 thickness case. So that was an unexpected but interesting result. Then finally, in the cyclic testing, we found that without adhesive, and for the most part in the 3 thickness cases, because they didn't benefit from adhesive, the solid rivet equaled or exceeded the performance of the resistance spot weld baseline. The case where it didn't were in the two thickness joints, joints 1 and 2, with adhesive. And I want to point out here that because we had adhesive in this joint, we used a much higher force than we did in the non-adhesive joints. So this doesn't mean that adding adhesive made the joint perform worse, but we had to increase the load substantially to get a failure. So it's only underperforming compared to resistance spot weld with the same load. And in this case, it is because the failure mode changes at sufficiently high loads, it actually causes a failure at the joining element and not in the parent metals. Here are some example slides. These are the same three joints that you've been seeing throughout with the resistance element weld. You can see the joining element left behind in the upper left-hand picture, for example. So there you can see we have pulled the joining element out of the top sheet, which is more or less what we would expect. In the upper right with structural adhesive, we actually see a failure at the interface to the joining element rather than in the top sheet because there's a stress riser there. And then in the bottom sheet, the failure mode is a little bit different than the resistance spot weld baseline because we are cracking through the weld surface instead of pulling a nugget out of the bottom surface. And the cyclic loading is actually relatively similar, but again, seeing a little bit more of a brittle mode. We are actually seeing a failure at the interface of the joining element in the two thickness joint, similarly in the two thickness with adhesive joint, and we are actually pulling a nugget out of the bottom sheet in the three thickness. Here is the data summarized for the resistance element welds. Again, these are the same three tables, the same 6 joint configurations. We do have 2 columns because we had 2 different suppliers for the resistance element welds. And we're just calling them type C and type G in our case in order to anonymize these suppliers. The effect that we found is in two thickness joining, the resistance element welds actually work well and were directly comparable to resistance spot welding. In the three thickness, it was a lot more sensitive to the bottom sheet thickness because with the resistance welding process, it's difficult to get a really good nugget between the mid sheet and the bottom. So depending on the exact stack, some of them were directly competitive with the resistance spot weld and others saw some reduction in performance, but were generally acceptable. For the energy at break, we saw mostly similar results. Anywhere where we had difficulty getting to a high peak load, we also saw a corresponding reduction in energy absorption, largely linked to nugget size. We did see some differences in adhesive performance for energy absorption on the two thickness joints in particular, and that was again because the failure mode changed. We broke the coupon at the interface to the joining element instead of separating the top sheet. So that is not unexpected. And in cyclic fatigue, what we found was that generally speaking, on the two thickness without adhesive, they were competitive. In the three thickness, we had the same difficulty as we did with peak load and energy in that the smaller nuggets in the bottom sheet in through thin material did see some degradation in the cyclic loading. And in the case of the adhesive, we saw a change in failure mode in the two thickness that saw some reduction in life. The final joining method I'm showing today is the friction rivet, and you can see that we only have the two thickness joints because, as I had mentioned previously, the technique only works for two thickness joints. On the left, we see a pretty typical tear through like we did with the resistance spot weld. On the right, with adhesive, it was again very similar to resistance spot weld. In cyclic, we see, and this is a typical theme we've seen with the mixed material, many of them cause a cyclic failure at the interface to the joining element because there's a stress riser there. And this is the tabulated data. In general, the friction rivet worked well for 2T joining for peak loads. We did see some reduction in energy absorption depending on the size of the interlock with the joining element and how much energy it took to tear it through the top sheet. And in the case of the cyclic loading, in the cases with adhesives, because we changed the failure mode from the top sheet to the interface, we saw some reduction in performance there. We also took each of the configurations and ran them through a cyclic corrosion in order to establish whether we had mitigated galvanic corrosion potential. These are the resistance spot weld baselines, and as one would expect, there is no significant corrosion issue with it. This is the solid self-piercing rivet, so there's a little bit of cosmetic corrosion, a little white corrosion around the insert, but nothing that was significant structurally. These are resistance element welds. Again, you can see the outline where a little bit of white corrosion is coming up around the steel element, but there's no red rust or degradation to the joints. And the friction rivet actually also shows no real effect from the corrosion testing. So all three of these mixed material joining methods can reasonably be said to have mitigated the galvanic corrosion concerns. So our conclusion for this was first, from a two thickness standpoint, all three of the technologies performed adequately for our needs. For three thickness joining, both the resistance element welding and the solid self-piercing rivets worked, but there is a caveat that they are somewhat sensitive to the stack up. So the stack-ups will have to be validated for any given application. That's not really any different than resistance spot welding is, though. And an interesting outcome, as I mentioned, was that the solid self-piercing rivets were actually substantially higher in energy absorption than the resistance spot welding baseline. So that's led some interesting avenues of research in some of our ongoing projects, which you'll probably hear about in next year's presentations. Recommendations for going forward, I would like to study a little bit more how we can interact with the adhesives, because we found that the mixed material methods did not work as well in the adhesive joints as the resistance spot weld did. So it would be advantageous if we could find a more optimal way to make the mixed material and adhesive play nicely together. And there are some emerging technologies that were not far enough along when we started this project, but have gotten further since, such as thermally assisted clinching and thermally assisted self-piercing riveting, that I would like to see tested as well and added to our database. As some of you have probably already asked, to get this presentation, you can download it from autosteel.org. We've also included my contact information as well as Wendy's. If you have any additional questions after the presentation, you can contact us, but I will yield the floor to any questions you may have submitted during the presentation.
Thank you, Brian. Yes, we have several questions actually. Donald Jordan asked several questions.
All right.
The first question being, unmute Donald in case is the steel uncoated, e.g. GI, GA? Is it coated?
All of the steels were coated. I believe they were all GI, except for the press hardened steel, of course, which is aluminum silicon.
All right. The next question he had was, does the aluminum have a mill applied pre-treatment?
I don't want to give you an inaccurate answer. I don't off the top of my head recall if it was pre-treated from the mill as we used it. I don't believe it was, but I would have to double check that.
Brian, this is John Carroll. I can help out. Yes, it was. Okay. It did have the coating that comes from the mill. Yeah, I actually procured the aluminum, so yes, it did.
Okay. Thank you, John.
His next question was, what is the mechanical test failure mode for the various sealers after corrosion tested, i.e. after degradation of the sealer?
That's actually a good question. In this case, we did not continue and retest them after corrosion. So our corrosion was at this point just a visual inspection to see if we were getting red rust from the joints. We did not study how well the adhesive or joint otherwise residually held on to the aluminum sheet. That's more of an adhesive study than what we were studying here.
Okay. His next question was, is the PHS coated? If so, was it thermally treated, fully treated?
Yes, of course. The PHS was aluminum silicon coated, and it was heat treated with standard process parameters so that the aluminum silicon diffusion coating was within our normal specifications.
Okay. Then he has, please have this, let's see here. How do you know there was no galvanic corrosion unless you disassemble the joint?
We did disassemble some of the joints, and there was a little bit of corrosion where the E-coat didn't cover them because they were E-coated after they were assembled. But the galvanic corrosion we were looking for was specifically between the joining element and the top sheet of aluminum, because we had sealer in the rest of it, and so it essentially didn't see any of the corrosion environment.
Which accelerated corrosion test did you use, and where the fang interfaces mounted horizontally collect water or vertically drain well?
I believe it was SAEJ 2334, and they were slotted in vertically, I believe, to fit more into the corrosion case.
Okay. Then we have another question from Mark Van Alstein. Did any of the values significantly exceed RSW performance, say 120% for load or energy at break? You mentioned the cyclic loading.
Yes, the energy at break for the solid self-piercing rivets were more than 120% of the resistance spot weld baseline.
Okay. Next question, will the rivet with adhesive pass if the load is the same as RSW?
I'm not entirely sure I understand the question.
All right, let's see here. I cannot seem to unmute if they're on the web for some reason. Tracy, do you know how to unmute them? Let's see if we can get this question clarified.
Wendy, this is John. I don't think the main audience can ask directly, but Brian, I think I can clarify this. At some point during the presentation, you said that if you increase the load because it was an adhesive joint. I remember that, and yes. I think the question is, had you run the two joints at the same load, would they have been equivalent? I think that's what they're trying to get at.
Well, yeah, certainly when we ran the joint with just the sealer and not the adhesive, they performed fairly well in Cyclic. So I don't think that would be a problem. It was just the particularly high loads we saw with adhesives where we saw a significant divergence in the Cyclic load performance.
And that's probably due to the material itself now rather than the joint, Brian, probably, right?
Well, there are a couple of things going on there, but there is a stress riser at the joining element. And depending on the amount of load and the modulus of the adhesive, you'll see more or less localized strain at the notch for the joining element. So it really depends on how much localized strain you're seeing there versus the fatigue property of the aluminum sheet.
Yeah, I think that helps clarify. Thanks.
Thanks, John. The PHS material was the PHS material standard strength and not one of the newer high strength grades?
Yes, it was the more typical grades that are currently in volume production in automotive.
Let's see here. Did you use any virtual simulation to support the analysis?
No, we left the virtual simulation to our joining suppliers. In this case, we were taking things that our joining suppliers told us based on their analysis should work and then testing them.
What is the most important factor used to determine the performance of the joint, peak load, or energy absorbed?
There is some debate as to whether what is the most important factor for joining. And so we evaluated both the peak load and the energy absorption. So we covered both bases, but I don't think you're going to find a consensus on which is really the most important.
Okay. And then our last question, it looks like, would it be worth running peak load case?
I'm not sure I follow the question.
Richard Fleshner.
It's a peel load.
Yeah.
Load.
Oh, peel load. Okay, we did do some
I'm sorry.
peel test. Okay, we did some coach peel testing in phase 1. And what we found was we did lap shear, cross tension, and coach peel in phase 1. And what we found was that with the lap shear and the cross tension, we got fairly high quality data that was useful for analysis. With the coach peel, we saw a lot of noise in the data, and we felt that there was enough noise in the data because of the difficulty of assembling a really repeatable coach peel sample in very high strength materials that we didn't find it all that useful for analysis. So we ended up focusing on just the lap shear and cross tension for phase 1. And then we went to phase 2, we focused just on the lap shear because that was realistic to do a cyclic fatigue test on.
All right. Will simulation methods be developed?
I would imagine our joining suppliers who provided these various joining methods already have varying levels of simulation. They will probably continue to develop that, but simulating the creation of the joints is outside of the scope of our project.
Would you consider texturing the joint interface of both materials to maximize wetness of both sealer and adhesive?
That would be potentially in the scope for a future project. As I had mentioned, I'm interested in seeing how we could improve adhesive performance with the mixed material joining. That it could be one of the potential options for doing so. I'm not entirely sure how much we can improve it because there's always going to be a knock effect from having a joining element, but I think it'd be interesting to do some more research on it, yes.
Please comment on what the various combinations might to the tool life and energy consumption.
Well, tool life, in this case, tool life is not a really big consideration because the joining elements in each case are expendable. So we only use one joining element per joint. So for example, with the solid self-piercing rivet, the cutting edge of the rivet is only used once. So there is more force required to go through a thicker joint. So that probably has some implications on equipment life, but studying that goes beyond our scope, so I can't give you an exact answer.
All right, we've got, with the increased load applied and an adhesive, could you add a % increase number to the cell to show how much increase is sustainable before separation from the RSW in place of just showing the cell as red?
We have the information to do that, yes. For the publicly distributed version of the presentation, we are not prepared to share all of the information that we have.
That looks like all I have for questions. Tracy,
Right, well,
would you like to have closing remarks?
All right, this is John Catterall. I'm up next. Just to, I want to thank Brian and the team that did the work and put on the webinar today. I think we had a very productive half hour and a lot of good Q&A. Looks like we had pretty good attendance, a couple of hundred people. a lot of people that we know already, which is good to see, and some really good questions there. As we said, the information will be available on the web, and you can see that throughout the presentation here. What I'd like to let you know here, we're actually going to do another one of these webinars on Tuesday, July 28th. We're going to have Mike Karagoulas talk about liquid metal embrittlement. So please join us for that. The registration information, I think, is already up on autosteel.org, which is where you can also find all the information from today. So I think, do we have any more slides there, Brian? I think this might be our parting slide. Do you want to click one more? There you go. So just go back. So I'd like to thank everybody for joining today. Appreciate your attendance, and look for a couple of more of these webinars as we move through the summer here. So thank you very much, and goodbye to everybody.